Alright, so this is going to be kind of a short video. It's just going to be to introduce you to a new equation that we have, and this equation comes from Newton. So this is sometimes known as Newton's fourth law, but it deals with something known as universal gravitation. Okay, universal gravitation. So basically what that means is that, hey, we've been figuring out the force of gravity for a while now. It's mass times little g. Little g is 9.8 meters per second squared. It turns out that 9.8 meters per second squared is not necessarily the same everywhere on planet Earth. If you go a little bit higher, if you go a little bit lower, that 9.8 actually fluctuates a little bit. And it turns out if you go to the moon, then the moon is actually less. It's something like a sixth of that, like 1.6 meters per second squared. So there's got to be something going on to why this acceleration that we feel here on the surface of planet Earth is 9.8 while it's different elsewhere. And Newton had that same idea. He thought about why would it be the same or different, and he actually developed this equation from a totally different question. He wanted to know, why is it that the moon doesn't just fly off into space? Why is it that the Earth keeps hold on it? And it turns out the answer to that is gravity. So he developed an equation that talks about the force of gravity between two large bodies. So if we have the Earth, and that's a great E there. Okay, here's the Earth, and the moon somewhere over here. This is not drawn to scale. If you know anything about me, you know that the scale of the solar system is kind of a big thing for me. Anyway, so the two forces here. The Earth pulls on the moon pulls back on the Earth. This is actually Newton's third law. But what is that force? It's the force of gravity. Turns out that the equation is, the force of gravity is big G, I'll come back to that one in a second, times the mass of the Earth times the mass of the moon divided by the distance between them squared. And that R does not mean radius, it means separation. It's just the distance between them. Okay? So what is that big G? That big G is a constant. It's the universal gravitational constant. So we've been calling little g because we have this big G that comes up now. So big G is a constant. It is 6.67, that is a point, times 10 to the negative 11th. Wow. Times 10 to the negative 11th. Has a weird unit, newtons meters squared per kilograms squared. Yeah, weird. That unit is only there to make sure that everything works out fine when we multiply by a couple of masses and divide by a couple of meters. So let's just practice using that for a second. Okay, so the mass of the Earth is 5.98 times 10 to the 24th. And don't ask me why I know it, I just do. The mass of the moon is 7.35 times 10 to the 22nd kilograms. Don't ask why I know it, I just do. And the distance between them is 3.84 times 10 to the 8th meters. Don't ask me why I know it, I just do. Alright, so all that's going to go into our equation of Fg equals big G, m1, m2, that's the Earth and the moon, divided by the distance between them squared. Alright, so let's put all of this together. Okay, and then we're going to shove all of those into that formula. And here we go. Alright, so 6.67 times 10 to the negative 11th newtons meters squared per kilograms squared times 5.98 times 10 to the 24th kilograms, sorry about my handwriting, I'm trying to be small, times 7.35 times 10 to the 22nd kilograms divided by 3.84 times 10 to the 8 meters squared, and you get basically 2 times 10 to the 20th newtons. How do I know it's newtons? Because the kilograms squared cancels with these 2 kilograms, the meters squared cancels with those meters squared, and you're left with newtons. And that is a huge amount of force, but that's the amount of force you need to keep the moon kind of bound to the Earth. Alright, so that's just a real basic way of using this equation. We're going to talk more about where this equation came from as we get further in class.